Hello, and thank you for joining us. Welcome to the second Richard M. Karp Distinguished Lecture this semester. My name is Peter Bartlett. I'm the Associate Director of the Simons Institute for the Theory of Computing. We established the RMK series to celebrate the pioneering role of Simons Institute founding director Dick Karp in theoretical computer science. Formerly, these were known as the Simons Institute Open Lectures. They feature visionary leaders in the field of theoretical computer science on topics associated with current programs running at the Simons Institute. And the series is geared towards a broad scientific audience. We're grateful to the many contributors to the Richard M. Karp Fund who've made this series possible. So this semester, the Simons Institute's hosting two programs, one on probability, geometry, and computation in high dimensions, and one on the theory of reinforcement learning. And I'm delighted to welcome our speaker today, Professor Claire Tomlin, who's participating in the reinforcement learning program. Claire is Professor of Electrical Engineering and Computer Science and holder of the Charles A. Dassault Chair in Engineering here at UC Berkeley. She received her PhD from Berkeley and was a professor at Stanford for 7 years before returning to Berkeley as a professor in 2005. Claire is famous for her work in hybrid systems and control in safe learning methods that combine tools from machine learning and control theory and in applications in air traffic control and unmanned aerial vehicles. She's been honored with the Donald P. Ekman Award, the IEEE Transportation Technologies Award, and an honorary doctorate from KTH, the Royal Institute of Technology in Sweden. And Claire is also a MacArthur Foundation Fellow, an IEEE Fellow, a Fellow of the American Institute for Medical and Biological Engineering, and a member of the National Academy of Engineering and the American Academy of Arts and Sciences. So delighted to have Claire talking today. Her talk is titled Safe Learning in Robotics. Welcome, Claire.
Thank you. Thank you very much, Peter, for the invitation, and thank you to the Simons Institute. It is an honor and a pleasure to give this talk, especially this talk named for my colleague, Professor Richard Karp. Today, I'd like to talk about safe learning in robotics, and I'd like to bring a control theoretic viewpoint to the problem of learning in large-scale systems where there's a lot of new data available for use, yet the dynamics and the constraints and the safety criticality of the problems are very important. All right, let me just see how this is not advancing. Good. So as I said, I'd like to start by talking about some of these large-scale systems. And for throughout my career, in fact, since I was a PhD student, I've been working quite closely with engineers, scientists, and developers at NASA Ames who have been interested in developing new tools, models, and methods for doing air traffic control. And this is a wonderful problem. I'm just showing a snapshot of some of the data across aircraft across the United States. And then on the bottom left, a movie showing a few hours of aircraft coming into and going out of the Bay Area airports. So this is a system in air traffic control where there is a lot of new data available, data about routes, about weather, about other aircraft in the system. There's also new emerging applications, which is making the air traffic system a lot more interesting. The use of small aircraft, air taxis, and what I've pictured here are the potential uses of delivery drones, which have to fly through the air traffic system. And in all of this, safety is critical, but it's a system where there's a share of control between what will be automated or what is automated now and the humans, the people who are involved in the control. So there's maybe simplicity is the wrong word, but there's a sense that the system has to be understandable. Any automation that's being performed has to be understandable by the people in the loop. And learning, using modern AI and machine learning tools makes a lot of sense in this system because as I said, there's a lot of data about these systems, real-time data that can be collected. And so it's exciting to think of adaptation. So how one might adapt the current control methods or a current control policy as new data comes in. And so we've been working for years, as I said, with NASA, and we've just started a new project with NASA trying to investigate how machine learning can be used in this next generation air traffic system. And these are just two companies in the Bay Area that have been hiring some of the students from our research groups who, these are vehicles. On the left is an air vehicle, on the right is a delivery vehicle that is an automated vehicle. So there's no people in either of these vehicles, but they're systems that are in a sense, they're as close to fully autonomous as we can imagine. Using their sensors on board, they perceive the world and they react and interact. And importantly, they react and interact to environments where there's a lot that's known about the environments that they're operating in, but there's also a lot that's unknown, especially around the people that are interacting in the environment with these vehicles. So here's another example of safety critical vehicles where we're very interested in understanding how to incorporate machine learning tools. So today's talk has two pieces. The first piece, I'm going to introduce a tool that we've been developing for now, well, the past couple of decades we've been building on in my research group, which is a method for respecting constraints within a control system, how you verify that a control system respects those constraints, and how do you design control systems such that constraints are respected. And that's a tool called reachability. It's an old idea, and we have built on that idea and built a toolbox or a number of toolboxes of methods to verify and design controllers. And for the second part of the talk, I'm going to incorporate machine learning into this methodology and show steps of how one might approach incorporating such data-driven methods into such a safe control structure. So let's start with a kind of conceptual diagram. And here I've pictured, and I'm going to use my mouse, and I forgot to check this, but can people see that I'm my little mouse on the screen? Right now I'm circling the differential equation x dot is equal to f of x ud.
Yeah, we can see that. Okay,
great. So this is a diagram, a sort of again, a stylized picture. Suppose that this slide represents my state space X, for example, and I have some dynamic system that's evolving. Let's just suppose it's governed by a differential equation, x dot is equal to f of xu. And so u might be the control inputs that one, either the person that's interacting with the system or the automation can manipulate. And then we also allow for some disturbances D in the system that we can't control, but we assume that we know some bounds on those disturbances. Suppose one has a sense of what it means for this system to be safe or unsafe, and suppose that that safety or unsafety can be represented as remaining either within or outside a subset of the state space of the system. And this is the set here that we labeled the set G at time 0, that red ellipse that I'm showing. So the backwards reachable set, which is shown here in pink, so the backwards reachable set for a particular time horizon t, which we'll call G of t, is that set of all possible states for which, for all possible control actions u, there exists a disturbance which could drive the system into that unsafe set within t time units. So that means that if we call, suppose in a control system where we're interested, for example, in collision avoidance. So that's one of the first problems, example problems that I'll show you. So collision, in the air traffic system means that any pair of aircraft comes closer than a certain requisite distance. So that's separation, loss of separation. So we can represent collision as some subset of the system state space. And then this red region, this backwards reachable set, could then encode all states for which, despite the best possible actions of the aircraft, the maneuvers that they can make, the dynamics of the system coupled with unknown disturbances could drive the system to unsafety. So the point is that if this set G of 0 represents an unsafe set, then this backwards reachable set represents states for which you want to make sure you avoid, because if you get into those states, it's and you know the disturbance, for example, does do its worst possible action, the system could go to unsafety. So I sort of used a terminology that makes us think about a game, the best possible control actions for the worst possible disturbance under these dynamics. And in fact, we use game theory to compute or to characterize and then compute these reachable sets. It's like we're pitting the control against the disturbance as players in a game, and we pose the problem as a game. The best possible actions of one player are not sufficient to protect against the worst possible actions of the other, so we're going to label that state as unsafe. And so that set itself is interesting, and that's something we're after to compute, because if we could compute that, then we could ensure that if we stay outside of that set, so in this blue region here, that we'll keep the system outside of the unsafe region for at least t time units. All right, so that's the value of a backwards reachable set, and that kind of describes in words what it is. We've worked on developing a theory for computing those reachable sets, and we've shown that, and us and others have shown that that backwards reachable set can be expressed implicitly as the sub-zero level sets of some value function j of xt, where j of xt is the solution to this what is called a Hamilton-Jacobi either Bellman or Isaacs equation. We usually call this a Hamilton-Jacobi-Isaacs equation because Rufus Isaacs is responsible for some of the original work in dynamic game theory. And when we're using this combination of control and disturbance as two players, we're posing it as a game. It's a little bit different than a standard Hamilton-Jacobi PDE because we have this min with 0 on the right-hand side, and that's important for reachability. It basically ensures that once a state has been labeled as unsafe, it doesn't become safe at a future time. So you can't, for example, start out at a state and over the time horizon go through the unsafe set and come out the other side and therefore label that state as safe, because at the end of the time horizon, it's outside of the set. You don't want trajectories from states to even go through that set. And that min with 0 ensures that, that you're computing the full reachable set. Okay, so the idea then is, well, the idea that we asked is, could we compute this set via some kind of Bellman iteration process applied to this Hamilton-Jacobi equation? And really, you know, sort of maybe diagrammatically with this stylized diagram, what we're doing is we're taking the, you know, the states on the boundary of that set at each iteration, and we're asking, are they safe for the next epsilon time units? And if not, we propagate the boundary of the set backwards. And so if we had a vector field here that's in general pointing to the left of the screen, then the backwards reachable set would propagate backwards to the right. Okay, so that's the general idea. We have a way to characterize the set implicitly through a value function, and we also have a way to describe the, you know, the equation that we need to solve to compute it. Now the challenge is computing it. And so we've from the beginning, we started using level set methods, which were developed by Stan Osher and Jamie Sethian. And John Tsitsiklis in sort of different groups. And so the idea, and here I've pictured it from a side view, is that set, if we characterize that set as the sub-zero level sets of a function, then at the bottom I've shown what, you know, a slice of that function might look like. And so initially we have a set here, here's the slice of that set, whose sub-zero level sets represent that ellipse. And then over time, we're taking that function j of x t, and we're evolving it according to the Hamilton-Jacobi-Isaacs equation. So we're maintaining the sub-zero level sets of the evolution of j. Okay, so a few points here that are going to come up again later when we introduce machine learning. So if the set is controlled invariant for all t, that means that if after some finite time horizon, that set, or whatever that time horizon is, that set closes off and it doesn't grow anymore, then any super zero level set of that function is also invariant and may be used to prove safety of a control system. So that's kind of intuitive. If you can stay outside of a super zero level set, so if you can stay outside of a set that is guaranteed to contain the set, then you're staying outside of the set itself, if that set does represent an unsafe set. And then the other thing is that even if the disturbance were known, there still might be some volume in that set, right? Just coming from the dynamics. You can imagine if you're riding a bicycle towards, there's a tree in front of you, then, despite like the maximum control effort, turning to the left or turning to the right, if you're too close to the tree, you're still going to hit it, right? But if the disturbance is known, then we could theoretically compute the optimal reachable set, the smallest unsafe set, for example, that just is a result of the dynamics itself. Okay, so in terms of computing them, that, as I said, is a big problem. And that's been a challenge that we've been working on in my group and other groups for a long time. We, as I said, used the concept of level set methods, which generally are methods to compute solutions to PDEs, governing. Before we started working on it, most of the methods have been applied to equations which govern one fluid flow through another material, for example. So we applied this to control systems, and so here you can see one of our control system examples. It's sort of an interesting shape here. But it's, the final function looks like this over part of the domain, and we're capturing the sub-zero level sets of that function. What's interesting about this? Well, the boundary of the region, the boundary of that set, is defined implicitly by the zero level set of that function. And then anywhere away from that function, so if we're using, if we use a signed distance function for j, for example, then the magnitude of j at any point is the distance from that state x to the boundary, whether you're inside or outside. So if you're inside, j is negative, and outside, j is positive. And this is all interesting information for control, because often, we don't only want to know, whether we're at the boundary and we have to apply a safe control to stay out, but we want to know whether, how far we are away from the boundary. Okay, so at the bottom, I've provided two links. These are references. Ian Mitchell was my first PhD student at Stanford. He's now a professor of computer science at the University of British Columbia in Vancouver. And we worked on the theory of this together. And then when he became an assistant professor, he coded up what he calls Toolbox LS. So this is a level set toolbox for doing some of these computations for a number of different control, continuous control and hybrid system examples. And it's well documented. You can download the toolbox. It's written in largely in MATLAB, and it's got a graphical interface in MATLAB. And since then, we've been working with a number of my, my students, in particular Mo Chen, who's now a professor at Simon Fraser University, also in Vancouver, and Sylvia Herbert, who's just finishing her PhD this year and is going off to UC San Diego to be an assistant professor, and others, to develop a C++ implementation of the level set toolbox, as well as a bunch of useful kind of wrappers to enable, to do like sort of an easy interface with the level set toolbox. And I've provided a link to that, the C++ implementation of the level set code there. Okay, so here's one example. This is when I was, maybe some of you recognize, this is a field at Stanford. So this is when I was still at Stanford, but I like this example. There's there's 4 quadrotors. This was back before you could buy quadrotors on every street corner. And we built these ourselves with the onboard computers and carbon fiber tubes. And there are 4 students there, and each is controlling via a joystick a single quadrotor. However, when the quadrotors get closer than their reachable set distance, and on the right I've got a snapshot of each quadrotor with the reachable set for collision for that aircraft, that quadrotor, with each of the other 3 aircraft around it. So when one quadrotor comes within the safety distance, the reachable set distance of another quadrotor, the onboard control takes over and guides the vehicle away from each other. And what's that control? It's simply that max over u from the Hamilton-Jacobi equation, which not only gives you the reachable set, but it gives you the best control to use at the boundary of the reachable set to ensure that the vehicles don't lose separation. And so the automation takes over, guides the vehicle away from the vehicle that it's potentially in collision with. And then after a little bit, the control is passed back to the human, the student who's joysticking the vehicle around, which isn't the best interface, but it's more of a test of implementation of this method. And this was kind of fun because the students were trying to, they're trying to cause collision, and basically this reachable set acts like an invisible field that keeps the vehicles away from each other. I like this example, even after so many years. I think it's quite illustrative of the method and the fact that we can run this in real time. If you can do set avoidance, you can also do set capture. You just change the role of the min and the max. So now you'd like to reach a desired set despite disturbances which may be pushing you away from that set. So we call that a capture basin that we want to compute. The backwards reachable set is the capture basin. It describes the set of states for which there exists a control that you can get to that desired, so you can get to that desired region while despite disturbances that may be trying to push you away. It's a Hamilton-Jacobi-Bellman equation. The only difference is that the min and the max role have been flipped. And you can piece these together. So not only can you, so you can piece these together in a couple of ways. First of all, you can compute reach avoid sets. So sets of states which reach a target set while avoiding an unsafe region, while maintaining constraints. And then you can think about a hybrid system where you're switching between different modes, maybe different dynamic behavior, which we use a lot in aircraft control, for example, when we're switching between a capture altitude mode or a landing mode, or in collision avoidance, when you're switching between a regular following path mode versus avoiding another aircraft. And so here we've got 2 different flight modes, and we can string this together. So we'd like to end up in a target set. And so we compute, first of all, the capture basin for the capture basin for the ultimate target set. So in that way, we can kind of back chain these reachable sets, all the while avoiding unsafe sets. And what's nice is when you define these sets implicitly in terms of these functions j of x t, so the functions in one higher dimension, the computation becomes quite intuitive. I mean, it's still a Hamilton-Jacobi equation. We still have to deal with the curse of dimensionality, which I'm going to talk about for a few minutes. But things like reaching one set while avoiding another is just in those sets. It can just be computed like a mask. You compute one set and then you mask out another set, and that becomes a constraint that I'm showing here, like subject to, for some reason, everybody maybe can see my mouse except for me. But we set up what's called a variational inequality, where we're computing the solution to that PDE subject to the constraints of avoiding the unsafe set. Okay, so dealing with the curse of dimensionality, this has been a big direction in my research group. I would say, in terms of our research now, and working in reachability and safe learning, probably about half of the work is in trying to do computations like this efficiently in high dimensions. And then half of the work is in methods to incorporate machine learning for data-driven, so for systems where you only know part of the model or you only know part of the environment and you want to learn that as you go. So, and it's, there's quite a big community working in these types of tools. And I've listed just some of the work that's been doing, and people have been approaching the problem of cursive dimensionality in many different ways, sometimes very practical ways. Like if you have a bunch of vehicles on the road, that's a very high dimensional problem if you think about the multi-agent collision avoidance problem. So impose some practical constraints. You put roadways in the air traffic system. There are highways in the sky so that the vehicles are lined up against each other, and you really only have to consider constraints with respect to the vehicles that are closest to you. A lot of work in approximating or over approximating reachable sets, by approximating the sets, approximating the dynamics, and using simpler representations of sets and dynamics than just, say, a level set function of a complicated Hamilton-Jacobi equation. Methods that we've also contributed to on decompositions. How might you take a high dimensional system and decompose it into a bunch of low dimensional systems, compute the reachable set in the low dimensional system, and then use that to compute either an exact or over approximate representation of the reachable set in the high dimension. And I'm going to briefly mention the last two projects that we have, because they're quite recent projects. And the last 2 points this morning, one is, how might you exploit offline computation? If you could compute a reachable set offline and use it online, that's a promising method. And then the second is something that really has been, over the past few months, we've actually been trying to use machine learning to compute solutions to these Hamilton-Jacobi equations. And I just want to mention that very briefly. I think it's quite exciting. So this set of examples comes from the PhD work of Mo Chen and Sylvia Herbert, and several others. Actually, I'll reference the others. But the idea here is that if we could, and I'm using the context of now robot path planning, well, robot or autonomous vehicle path planning, and suppose that we had this reachable set tool, but we couldn't compute it in real time because our dynamics were, perhaps they were high dimensional, like the quad rotor over on the left. But we had access to fast robot path planning methods for low dimensional models. And that's what I'm showing on the right in this fast but less accurate planning. Less accurate because we're using low dimensional models. But if we tried to use high dimensional models, we would have a very slow but accurate planning. So our proposal in terms of reachability is to use the model error, the difference between the high dimensional model of the aircraft and the low dimensional model of the aircraft, compute a model error, and then compute reachability based on that model error. Compute a tracking error bound. How far can the high dimensional model be away from the low dimensional model? And if we've pre-computed that, then we can carry that pre-computation around us while doing fast planning, because it gives us a principled error bound around our low dimensional planning model, which will ensure that if we compute a plan using the low dimensional model, the high dimensional model will always be able to track it, and what's more, stay within the reachability constraints. So I've described what the method is very briefly, and I have an animation that describes it. So the idea is we have these two systems, I'll call them planning and tracking system. And we'd like to be able to compute, say, over this particular value function, which I've shown on the right, the set which is, so the bound between those two models, which translates to the largest controlled invariant set within that value function, which is described by the distance between the two models. So what this diagram shows is a reachability computation. And so let me just say it more concretely, what I said in a fairly abstract way. that if, for example, you would like your planning model to stay within 0.5 meters of your tracking model, so that was the smallest set, there's no control given the models that we have in this particular example that will let you do that. Namely, there's no way with the models that we have that you can guarantee a 0.5 meter tracking error bound. But if you increase that to 0.75 meters, there is actually some volume in that reachable set. This purple region here, that's the region that describes those states which are guaranteed to stay within 0.75 meters of the fast planning model. And if you increase that bound to 1 meter, then there's an even larger controlled invariant set, okay, that's described on the right here. And so that's the reachability computation. That's how we compute the tracking error bound, and we determine what these minimum tracking error bounds can be when we're doing robot path planning in real time. So we've applied this. This is just a simulation showing 10-dimensional near hover quadrotor model. This is a good model of a quadrotor if it's sort of a near hover condition, and it's tracking a planning model, which is a 3D point source. So we can do very fast planning using that. So this is using RRT method, which is a fast, a very ubiquitous method used in robot path planning. Okay, so here the vehicle is the green star is the planning model. The box around that in 3 dimensions is a 3-dimensional projection of the 10-dimensional reachable set into the 3 dimensions of X, Y, Z. And that planning model is trying to get to the goal on the right-hand side, and it's being faced in real time with constraints that it detects when it's within a sensing bound. So that box around it describes the tracking error bound. It says that 10D model is always guaranteed to be within that box around the planning model. And so we can use that box for planning in real time because we've done that pre-computation. Okay, so we've tried this in a number of more complex scenarios. We've used it to switch. We've said, well, you're never going to get with this simple planning model, you're never going to be able to meet the small tracking error bounds you need maybe to go through narrow corridors. So that gives us an indication of, well, how about if we then switch to a different planning model, which is higher dimensional, but it gives us a smaller tracking error bound with the full dimensional tracking model. And so not only can reachability compute these tracking error bounds, but it can tell you exactly where you should switch to a higher dimensional planning model so that you can meet the constraints of the planning problem. And what's the cost of that? It just means that the planning becomes slower because you're using a high dimensional model. So it's like this planning fast and slow. When you're in wide open spaces, you can move quickly with a big tracking error bound. As you get into smaller corridors, you slow down because you need a smaller tracking error bound, and you can pre-compute these ahead of time. So this is the work of David Fridovich-Kyle and Sylvia Herbert and others, which we published in ICRA a couple of years ago. Others have used this. So we've teamed up with Alan Yang and some researchers from Shankar Sastri's group who have been using this method of fast planning and like computing a tracking error bound so we can do fast and safe planning in their augmented and virtual reality systems. And the idea, and I don't think I have time to show this video because I want to get on to the learning, is that the user, the person who's setting out the plan, can just put a rough sequence of waypoints out in the space, and then in the lab behind him is a quadrotor that's flying the trajectory set out by those waypoints using this fast planning method in real time. We call this method FasTrack, for fast and safe tracking. Okay, we've used this method also for doing something. This is sort of stepping now into learning methods for planning robot motions when there's quite an unpredictable environment. And as I said earlier, one of the most unpredictable parts of the environment are the people in it. So here is work that we've been doing in conjunction with Anka Dragan's group in EECS at Berkeley. And this work is assuming that the people in the environment, so in this, again, stylized diagram, we have a quadrotor that's kind of observing what the person's doing and trying to plan a path that must avoid the person and the trajectory that the person's taking. This is a model that's used a lot in the robot motion community when you're trying to plan robot motions around people. And it's a model of a person. So this is the quadrotor has this model of a person represented by this probability distribution or belief distribution of where the person is going to be, what action that human, the action of the human, the input of the human will take. And the model is, it's basically a Boltzmann distribution model, which, and here beta is that inverse temperature coefficient of the Boltzmann distribution. And it's a model that says, you know, if we model the person as goal-driven, like, for example, this person may want to get to the door, and we can model those goals ahead of time, then the actions that the person takes must be generally optimal towards the goal. Okay, so this is the model. And when we talk about optimality towards goal, it's it allows for some noisily rational model, that the person is generally moving towards their goals, but there may be some noise associated to it. Okay, so that's the model, and it's been used in robotics. It's been used in cognitive science as well as a sort of a decision theoretic model. So for example, in this scenario, the pink region would represent the regions of high probability that the person is going to move in, because if they want to move towards the door, modeled by this parameter theta. And then the blue regions would represent regions of low probability. If the human's moving towards the door, they're probably not going to veer off the straight line path. So we thought we'd use this with one caveat. This parameter beta is something that we can tune. It's a scalar. And as the robot is gathering information about its environment, about what the person's doing through maybe its cameras or its vision system, then it could update that parameter based on whether the person is being more rational towards moving towards the goal. That would correspond to a higher value of beta, or less rational. So if beta were 0, for example, this model is just a uniform distribution over all possible actions of the human. A human could sort of move in any direction. And so we implemented this using FasTrack for the robot motion. All right, so here's the scenario where the person turns around and maybe they've forgotten their keys or something, but the robot doesn't have that modeled. So the idea would be to update this parameter beta, and we update it according to this this Bayesian update that says, okay, well, the person is not rational towards the model anymore. Let's update beta. And so immediately the distribution of where the person could become spreads out. So we tried this out with FasTrack. And so here you'll see some movies. This is Sylvia. She's our human being in Sylvia Herbert, one of the researchers on this project. The other people are Andrea Baichi, Jaime Fizak, David Fridovich Kyle, and Sylvia. And there's a quadrotor, this little quadrotor that's just crashed into Sylvia is here. So the quadrotor, Sylvia is trying to move across the room to the door, but there's a coffee spill here on the floor. It's not a real coffee spill. We've just marked it out, but we put a little cup there to indicate it's a coffee spill. And the robot can see Sylvia's motion, but the robot doesn't know about the coffee spill. So the robot thinks that a rational model of Sylvia would be to move straight towards the door. And then as she moves, the robot can basically, you know, update her rationality, or actually what is, you know, we call now model confidence. It's our confidence in our model on what Sylvia is going to do. So let's play this video. Okay, so here Sylvia is standing at her initial position and she starts to move. What you see, these sets emanating out of Sylvia are just the next few steps according to this Boltzmann model. And this quadrotor sees, you know, you can see a top-down view of on the right of that same experiment. as Sylvia starts to deviate, the robot becomes less sure of what Sylvia is going to do, and immediately the distribution around her starts to increase because the robot updates beta to a lower value to indicate her uncertainty. Okay, and we've extended this, and let me just show this video quickly. It scales. So it scales to multiple humans, multiple robots. There's 2 quadrotors now. That's Sylvia and Jaime. Jaime is being a little irrational from the beginning, according to the model, because he's kind of moving slowly and dancing a little bit. But what's interesting here is that that model, that Boltzmann model, naturally takes into account the fact that when they come close together, they kind of stop and avoid each other. Then the robot observes that, and as beta is automatically updated to be a little more irrational because they're each not moving towards their goal, there becomes a larger region for the robot that's running this FasTrack algorithm with reachability to avoid. Okay, so this is kind of a demonstration of how you might use this reachable set methodology with a combined model of the environment in order to, and a single parameter update, so kind of moving towards learning, but not really learning yet, to do real-time motion planning. Okay, and just to say that Andrea Baichi has now taken these ideas and gone a few more steps further with other students in the lab, Samuel Bonsall and Ellis Ratner, to think about how one might actually use reachability to analyze things like the dynamics of that belief propagation. So could we, instead of doing a simple single parameter update, could we actually use reachable sets to compute things like what is the worst time to achieve a high confidence in the model? So now the dynamics that we're performing reachable set computations on are not just the human motion, they're our belief in our model of the human motion, which I think is very exciting and new. So we have 10 more minutes, and I'd like to finish a little bit early to allow some time for questions. So in the last 5 minutes, I'm going to say one more word about high dimensional sets using machine learning, and then just show you some of the results that we've achieved over the past few years in incorporating machine learning into these sets. So these are more example driven than they will be sort of the methodology. But what we've talked about so far is introducing this concept of reachability and designing methods which allow you to incorporate data in real time through some simple, well, not so simple, but through parameter updates on distributions and how you might use that in real-time motion planning. Computing high dimensional sets, reachable sets, is still, very challenging. And we've contributed to some of this literature, but the latest thing we're doing, and this is just hot off the presses, it's a new result that Samuel Bonsall has just been achieving over this past summer, is to use deep neural nets to actually do that Hamilton-Jacobi calculation. So you teach a neural network how to solve a partial differential equation. And I think it's just wonderful. Samuel has now computed a 9-dimensional reachable set without, the only approximation comes in now in the approximation that comes from the fact that you're using a trained neural net to solve that Hamilton-Jacobi equation. And what's more, we've been able to show that, in this light purple region, this is a 3 aircraft encounter. So 3 times 3-dimensional models is a 9-dimensional set. We've never been able to compute that directly before. These Hamilton-Jacobi grid-based methods go up to about 5 or 6 dimensions if you're lucky. Otherwise, you have to use all sorts of decomposition methods that I talked about earlier. But now he's computed an approximation to the 9-dimensional set, and he's shown that it captures states that are unsafe that we haven't been able to capture before. So for example, this red dot on the left-hand side in these light purple states, this is a projection of this 9-dimensional set, actually represents full, this is a 3 aircraft conflict that indicates that there is a loss of separation between the 3 aircraft. So we're quite excited about this and moving this forward. Okay, learning dynamic behavior safely. So I'm going to end with just maybe two videos, two experiments that we've done in recent years to show, how one might incorporate learning if you don't know the dynamics, or you know some of the dynamics but not all of them, or you don't know the environment, or you don't know the constraints on the system because you don't know the dynamics. So let's end with that. And so this is the first example in that realm. This is the idea that we have, we have a model of this quad rotor, and we're trying to make it go up and down, step trajectory up and down inside the room. But we, in terms of safety here, we want to make sure it stays within an envelope so that it doesn't, fly up too fast and hit the ceiling or come down too fast and hit the floor. So we call this envelope protection. And we have a model for the vehicle, and we compute the envelope given the constraints of the ceiling and floor and our knowledge of the limits on the velocity. We compute that envelope. And then in this experiment, we took the model away from the vehicle and we asked it to learn a control law. Okay, so the quadrotor first drops to the ground because it doesn't have a model of itself, so it doesn't have a control. But it doesn't hit the ground. We let it keep the reachable set that we computed originally. We just don't give it its model. And we used a very simple learning scheme, which is called policy gradient sign derivative here, inside that envelope. So as it hits the bottom of the envelope and it starts, applying a little bit of thrust, it realizes that by applying thrust, it can move up. It knows it can move up, so it knows it wants to track this, this blue dotted trajectory. And so over time, it uses policy gradient sign derivative within this safety envelope to learn to track that trajectory as best it can. So that's the learning. But what's constraining the learning is a safety envelope, which is based on a nominal dynamic model of the system. Okay, so it's a bit of an artificial example because we took the model away and we asked it to learn it. But it's sort of an example that shows a first step in incorporating machine learning into these tools. And what we've been doing over the past few years is to ask, and let me just skip these, is to ask, okay, well, what if you do learn a better model and you can start doing this? Can we actually learn constraints as they're updated? So what if something comes into our environment that we have to perceive and then protect ourselves against? And this is a first experiment that we did in that regard. And I think this will be my last my last sort of piece that I'll talk about before I skip to my conclusions. So here, in this second experiment of safe learning, we have again we have a quadrotor, and it's still trying to fly that up and down trajectory. So it's still trying to protect its envelope and not hit the ceiling or floor. But there's a disturbance. There's a big fan in the room that is not incorporated in the original nominal model of the quadrotor. And so let's just see what happens. We've run two experiments of this, and then we've superimposed them on top of each other. There's Kene Akamatalu, who was one of the key authors of this work with Jaime Fizak. So he turns on the fan, and the quadrotor comes down, and now you'll see the sort of separation between the two different experiments. As the quadrotor hits the wind field, there's two different quadrotors reflecting these two different experiments. So the ghosted out quadrotor is the one that's not scaling back its safety envelope based on the disturbances that it's measuring in real time. And it's not until it starts moving up away from the wind vector field that the two experiments start to converge again. So this methodology is basically updating the reachable set to a level set of a different level set of that function for which you can guarantee safety based on the current measure of the disturbances. Okay, so what we're doing now, and I'm going to end on this, is we're applying these ideas and extending them to how we might learn in unstructured environments. And so we've been incorporating computer vision into our control loops. And using deep neural nets for the computer vision part, so we're doing robot motion planning, learning about the environment as it goes, and we've wrapped a safety envelope around that. So if the control based on the vision algorithm is asking the vehicle to do something that's unsafe according to a constraint-based model we have of the system, then that action is pruned away, just like a standard reachability problem. And so those are some of the directions we're moving in now. Let me just skip to the end, to the conclusion slide. And conclude. Okay, so we've talked about safety from reachability analysis. We talked a little bit about the need for simplicity. So a sense of having a hybrid system model, which allows you to design a control system the way people tend to think about control systems in large scale systems. And we've talked a little bit near the end of the talk about how to learn from new information. So open questions that we're working on are, if you're in a safety critical scenario, how do you decide that you've learned enough so that you can update your reachable set, or you can update your control based on safety? How do we even model unstructured environments? These are questions we're working on now. We didn't get to talk about the last piece of the talk, which was how we develop a control law in unstructured environments by supervising the training of the vision convolutional neural net using optimal control. But that's one of the pieces that we're using there. And we've been working on other topics in this vein, like risk-sensitive reachability using the CVAR value instead of the J of xt value that we've been talking about throughout this talk. Okay, and I'd like to conclude with thanking many students and former students who've contributed towards this work, and also to thank the funding agencies who funded a lot of work. And thank you very much.
Thanks very much, Claire. That was a really fascinating talk. We don't have much time. If people have one or two quick questions, they can use the Q&A feature. I was actually interested in the use of these fast planning models in approximating the dynamics to avoid the curse of dimensionality. I wonder if there are cases where there's a similar role for the disturbance model. Trading off this sort of, I guess, conservativeness versus tractability of computing these reachable sets.
You mean for trying to represent a disturbance model?
Right.
Yeah, that is an excellent question, and that's been one of the focus areas of our research in the past few years, because that's been the part of the system. In those last few videos I showed, it's that disturbance model which we've been trying to learn. As you learn a better disturbance model, you can conceivably, you can become less conservative about reachability. And so that was our first take. Could we in fact learn more about the disturbances going on? And in those examples that I showed, they were quite well-behaved disturbances. They come in to be able to prove safety. You have to make assumptions like the disturbance is the vector field of the differential equation describing the system in each discrete mode is Lipschitz continuous in the disturbance. But under that assumption, we can update the disturbance. We used a Gaussian process model for the disturbance, and updated it so we could learn less conservative reachable sets. But I think you're asking a slightly different question. You're saying, could we provide a simpler representation, maybe some kind of structured representation of the disturbance, maybe with a few parameters that we could learn to be able to quickly update that model and get less conservative reachable sets? And that's something that I think is fascinating. And how to parameterize, how to define that structure is, I think, a research agenda in itself for these different types of problems we're interested in.
All right. Well, thanks very much, Claire. We're out of time, but fascinating talk. You've given us lots to think about.
Thank you very much, Peter, and thanks everyone for attending.
Thank you.